Okay, first of all, I want to give thanks to the organizer for inviting me, and also for giving me the chance to talk about this interesting topic that turns out to be related to many areas of mathematics. Like, let me just mention a few of them that are real analysis, geometric measure theory, functions of boundary variation, and also probability. Okay, before I start, I would like that you imagine in your head an open bounded set with the nicest boundary that's possible. Then we can ask what kind of geometric, how can we come up with a method to try to catch geometric properties of this set? That's where the spectral heat content and the heat content comes in to tell us how to do that. So, like I told you, we are going to take an open bounded set with a smooth boundary. We can imagine that it has holes. We will use the standard notation to denote the volume of omega and its surface area. Well, I'm assuming that, of course, the surface area is finite. On the other hand, we are going to consider particular heat kernels, such that for every alpha between 0 and 2, these heat kernels, and by heat kernels I mean integrable and positive functions, satisfies that the Fourier transform is given by the equation displayed at this part of the slide. So what is interesting about these heat kernels? They share two interesting properties. One of them is that they are radial. That means that they only depend on the length of the vector x, that is the variable in space. And on the other hand, they have a very beautiful scaling property, which when you are considering problems with integration, what that allows you is to translate the variable t maybe to another function and forget a little bit about the heat kernel. Now, it's very well known that for these heat kernels, it is a related Lévy process, who has transition densities given by those heat kernels, and they are called alpha stable processes. Those who are not familiar with these processes might be wondering, why are so many talks talking about these processes? And the reason for that is because I like to think in this way: they are like the siblings of the random motion, because they share many of the properties of the random motion, but they also have very different properties that make them unique. So what is the lesson here? Once you have some property that holds for the random motion, you should try to see if that property is also inherited by the alpha stable process. And like a siblings, like I said before, they will try to do the same as the random motion, and sometimes they do better than the random motion. Now, everything was born with the random motion, and the result that I have brought to you today concerns the Cauchy process. So this is a brother, and I want to compare what these two guys do with respect to bounded set of May. What I said before, I want to cache information by using the Cauchy process, because there are a lot of results involving the random motion. Now I just want to remind you, for alpha equals 2, we have the random motion with the very well-known heat kernel. And for alpha equals 1, like I said before, I have brought to you recent results involving this motion, and I just want to remind you that this normalizing constant is very well known, it's explicit, and I will use it later in my results. You will see it later. Now, like I said, I would like to cache geometric information about the set. One of the ways to do that is for an open bounded domain to find what is called the heat content associated to the alpha stable process. Well, what is this? It's only in the double integral over omega of the heat content. This is the analytic flavor. On the other hand, we have the probabilistic flavor of the problem of the heat content, which is like some kind of average of those probabilities where the process at time t is in omega and it starts in omega and the point x. So, like I said, my purpose is investigate the small time behavior of the heat content. And I will tell you in a little while why this problem is important. Now, the purpose of the talk is to present some results and conjectures concerning the behavior of the heat content and show some developments regarding the Cauchy process. Now, it turns out that the heat content was born when this function, which we call the spectral heat content, came about. Well, what is this spectral heat content? Is like an average of those probabilities for which the path of the process remains at the set omega up to time t. Okay? And I also have displayed a picture to show the different behaviors that the stable path have. In the case of the random motion, it describes continuous path, and on the other hand, for alpha stable process, we have a jumping process, jumping path. Now, what is the meaning of this spectral heat content? Basically, what it does is try to measure how fast the stable process escapes from the set omega. And I also want to point out here these red points. Those that are very familiar with this function may realize that these points that correspond the first time that the process hits the complement is implicitly contained in this quantity. And just want also to remark that this implies that if we want to cache geometric information with these processes, it seems that the alpha stable processor will be able to cache more information about the set omega than does the random motion. Why? Because the random motions only interact with the set omega, while the alpha stable processor will interact with omega and its complements. So we expect to see more geometric features for alpha stable processes. And we will see that later, that they do read more than the random motion does. Now, well, that is a question about why the term spectral. Well, the term spectral comes from the fact that given that our set is bounded, there exists, based on the spectral theory, an orthonormal basis of eigenfunctions, which that are, by the way, in L2 of omega, with corresponding eigenvalues, which are an increasing sequence of real numbers going to infinity. And this piece of information allows us to express the heat content in terms of the eigenfunctions and the eigenvalues. Well, this is the mathematical explanation for the spectral heat content. Now, I would like to give you a more easy way to understand this term spectral. Well, what this is telling us is that we have a countable amount of information about the set omega. What is that countable amount of information? The eigenvalues and the eigenfunctions. And the idea is to try to cache geometric information with these eigenfunctions and eigenvalues that let us figure out or how to perceive the shape of the set omega that we are dealing with. So try to see how that set omega looks like by using this information. Of course, there is no, this expression is not very useful to, at least I don't know if somebody has done it for using immediately this expression. Now, like I told you, everything was born with the random motion. And for the random motion, we have the following. This is a result of Vandenberg in 1994 and Prunker in 2003, that for smoothing of domains, we are able to retrieve the volume and the surface area of our set of omega. And here is very interesting the factor that we need to consider t squared, the square root of t. Okay? Now, what is interesting here? If we take a look, we have the spectral heat content here, and we have the heat content, and it is saying that they have a very similar behavior. Up to a constant, the same, the limit is almost the same. Now, one may wonder if that also happens for the alpha stable process. There is a relationship between the heat content and the spectral heat content. And it turns out that, according to some results that I have, that it seems that they are somehow related. I don't know very well how they are, but I can get estimates by using the heat content about the spectral heat content. Okay? So we see that the small time behavior involves geometric features of omega, and one of the applications, I have not given those applications here, but there are probabilistic tools that leads to classical isoperimetric inequalities once you have these behaviors. And we will see that some of the results also give proof of what is called the isoperimetric inequality for alpha perimeters. That was discovered like 5 years ago by Frank Rupert. And it's the statement is very similar to the classical isoperimetric inequality, except that we need to change the surface area of the boundary but for what is called the alpha perimeter, but we will see that later. So what happens in the case alpha between 0 and 2? So regarding the spectral heat content, as far as I know, the small time behavior is still unknown. So results concerning to the case alpha equals 2 seems to indicate that the small time behavior of these two functions should be similar. And the above facts motivates the study of the heat content, which is way easier to study than the spectral heat content. And one would dare to conjecture that the following limit, where we have the appropriate modification according to the alpha stable process we are dealing with, should exist. So 2 years ago I proved that this conjecture is only true as ln alpha is between 1 and 2 due to the following result. So for an open bounded domain with a smooth boundary, for alpha between 1 and 2 and with the right scaling similar to the random motion, we are able to cache the volume and the surface area of the set times a constant that only depends on alpha. Very interesting, because one could expect to see maybe the dimension involved in this constant, but it is not. It's very similar to the random motion case, which is not weird, because the random motion case, the coordinates are independent and everything, all calculation reduces to the one-dimensional setting. But it's also interesting here because it seems that, well, there is some kind of independency high there, but I don't know where. Now, for alpha equals 1, things change just a little bit. We were expecting t here. It turns out that is not the case. You need to multiply by log of 1 of t, and we still recover the surface area of the set, of the boundary. On the other hand, for alpha between 1 and 2, they have a uniform behavior, at least the second term. We have to divide by t. And we recover what I called before the alpha perimeter. The alpha perimeter was studied in detail by Rupert Frank, and he proved that there is an isoperimetric inequality also associated to the alpha perimeter. So, what is interesting here? Alpha stable processes are able to cache more geometric information so far than the Brownian motion. We have a non-local property. When I say non-local, I mean a quantity that involves both omega and its complement. Now, with these results at hand, and bearing in mind that the behavior of the heat content and the spectral heat content should be very similar, I was able to prove something that put in evidence the fact. Well, since I don't know if the limit exists, I only could work with the limit from the lim sub, but I proved that they should read the surface area of the set, both alpha between 1 and 2 and the Cauchy process, and they also read, in the case of the spectral heat content, the alpha perimeter. Okay. Now, the aforementioned results allows us to formulate the following conjecture for the cases alpha between 0 and 1. Because we already saw that conjecture was true for alpha between 1 and 2. So there exists a non-zero function depending on omega and alpha such that the following limit exists. This is apparently the right conjecture. For every open bounded domain with smooth boundary. Our previous result suggests that for alpha equals 1, the function we should consider is the one given in this identity. So the result that I have brought to you today is to prove that that conjecture for the Cauchy process is true. Unfortunately, I don't have the result for every open bounded domain with a smooth boundary. I only have the result for a certain class of sets. But I believe that these sets with a smooth boundary are contained there, and there is some future work to do that. So, but before I present the result, I need to introduce 3 more geometric objects associated to the set omega. Remember, we are trying to cache geometric information about omega, therefore we need to develop some geometric objects to try to see how they interact or how they appear in the asymptotic expansion of the Cauchy process. So one of them is what it is called in the literature the covariance function, which is defined as the volume of omega intersected by a translation of omega by y. Well, this is the first time, I saw this function many times in my courses of analysis, and I never knew how this object is going to be useful to me. And this is the first time that I find something where to apply it. And it turns out also for this problem, I would like to call this is like the DNA of the set of omega. Because all the information that I need to compute the third term, I will say later, of the Cauchy process is contained there. So this guy encoded a lot of geometric information needed to compute what I'm about to show you. Associated to this function, I will define R of omega, which is the smallest radius of the ball centered at the origin that contains the support. And also, these are 2 more quantities for every univector we define, and you can find this theory in the book of Maggie about sets of finite perimeter. what is some kind of directional derivative. They show in this book that this limited fit for the kind of domains that we are considering. A smooth domain, a bounded domain with a smooth boundary. And here there is a new object that I introduced, and I would like to call the problematic function. Because this one is the one where all the it involves this guy. It's very difficult to estimate or to know explicitly how this function looks like. And we had a really more complicated object involving that guy.
What is H?
H is the house door measure. The minus one house door measure. Because we are integrating over the surface area of the ball. So this is the result I have for the Cauchy process. If we have a domain which is bounded with surface area finite, and the troublemaker, my troublemaker function, belongs to the L1 space, when we integrate over 0, 1 with respect to this measure, then I'm able to compute the next term in the asymptotic expansion of the Cauchy process. So what is interesting here is the amount of geometric information that we have in this expression. If we take a look here, this is like the contribution of the Euclidean space. You can see the dimension D involved in that term. On the other hand, I have the radius of the smallest ball centered at the origin containing the support. I have the surface area of the boundary, also have the volume, also have the normalizing constant of the Cauchy process. And here, like I told you before, is where hidden information, I have hidden information about the set omega in this constant. Now you can see why I asked for this condition, to make sense of the constant C of omega. Yeah?
So gamma is something like a generator type, which is, can I see the definition?
Yeah. This?
Yes.
It's like, if you take a look, this is almost like this second derivative, order second derivative of the second order derivative of the, it's an asymptotic of the second order derivative of the covariant function. But I don't know if that function is smooth enough to say something about this quantity. Indeed, I believe that for convex sets, there is some kind of a smoothing influence over these functions. And that's indeed one of my future works. Try to prove the result for convex sets.
So G is generally kind of Lipschitz.
Yeah, it is Lipschitz indeed. Yeah. Yes, it is.
Okay, second order derivative.
Yeah. Mm-hmm. So, what is the issue with this theorem? Well, you may wonder, well, it looks nice, but how do you know that this is not empty? Right? So, I took care of that, and I proved that every ball of the radius 1, for every dimension bigger than 2, it is there. And I was also capable to compute, for the specific cases, d equal 2 and d3, the constants. On the other hand, I wanted to see how the geometry plays an important role in this constant, and I tried to figure out what was the constant for the unit square. Well, this is not unit, sorry, the square centered at the origin with side of length 2. And it is very easy to see what is the radius of the small ball that contains the support of the covariance function. Well, it took me a while. Indeed, I found an explicit form for the constant, but I used computers because it was very heavy work. That way we had computers to do that work for us, and I was able to compute explicitly the constant. Now, there are some open problems here. Well, this is the classical question. How large is the class W? If I can prove how large it is, at least is every open bounded set with piecewise smooth boundary contained there. If I can prove this, I will try to see what happens with compact sets, which are symmetric with respect to the axis, and if it is possible to obtain an expression for the constant. For example, it would be nice to consider regular polygons in the plane and see what happens. If we can get an explicit expression for the constant. And there is also another result that I would like to do is extend the result to the relativistic Cauchy process. Because it turns out the relativistic Cauchy process for a small time behaves like an alpha stable process. And for large time they behave like a Brownian motion. So this is telling me that maybe it's possible to extend the result for the relativistic Cauchy process.
You conjecture that will be the same result?
No, I believe well, it depends. You need to know what is the generator of the relativistic Cauchy process. It depends on another parameter called m, and I believe that parameter should be involved in that constant somewhere. Thank you very much. Okay. Well, very fast. Yeah?
With one-dimensional case, maybe
I did the one-dimensional case. I had results about that. I did, when I conjectured the results, I did it for the one-dimensional case. Nobody did it because they said, there's no geometry there. But it turns out that they had the same behavior, and that helped me to conjecture in the high-dimensional case. And also had a one-dimensional result for the spectral heat content. I found the second term for the one-dimensional case.
Does this heat content depends
Continuously.
Can be approximated over, say, set
That is a very interesting question, yeah, because one of the theories that is hidden here is sets of finite perimeters. Sets of finite perimeters are those ones that you can approximate from inside for sets that are that have a smooth boundary. And I believe that probably we can do some approximations using that theory. Like I told you before at the beginning, this is very related to functions of bounded variation. I still don't know how that theory could help us a lot to get better approximations, you know. It is there, it is hidden there. Mm-hmm.
Concerning the question, if you have a ball with a lot of small holes, that we see is a problem with the convergence. Yes. So what about this one-dimensional case? Did you consider just the interval or the interval holes?
Well, only an interval, A from B. That case that you are mentioning was done by, I think, Reminson and Kim recently, in the one-dimensional case, yes.
Do you have any interpretation of the limit in this Cauchy result in the end?
You mean, I don't know, why do you mean
it's
interpretation?
Not the surface area of the boundary, right? Does it describe something else?
Yes, I believe that it should somehow describe, like with non-convex sets, for example, I believe that they can describe the number of holes of the set. Or it could describe the mean curvature. I believe that they can do, and that is done, for example, for the Brownian motion. The third term of the spectral heat content for the Brownian motion is known, and we know that it recovers the mean curvature, and also multiplied by a factor d minus 1 over 2, so you can go also the dimension. And I believe that, yes, the number of holes, for example, for convex sets, it is there. Mm-hmm.
Well, I think maybe you could say a word on these things we have some results for potentials.
Schrödinger operator.
Find these full asymptotics.
Schrödinger operator with potential belonging to the Schwarz class, which is way different from what you do because you have a singularity at 0, and I believe that in other talk somebody talk about potentials that explode at infinity, which are really the one that we are looking for because they are sort of connected with this heat content. we want to study in more detail the potentials that explode to infinity.
More questions? If not, we have 20 minutes.